We're going to start off with this warm-up. Notice that your homework is a handout, and then on this warm-up you are asked if a series, an infinite series, converges. And we learned from the previous video an infinite series converging, right, is a sum that reaches a bound, right, an upper bound. And if your series is geometric, you can find its infinite sum. For reasons that are unclear, infinite series that converge are highly useful in further mathematics. So maybe you pause the video and go ahead and see if you can do these four without me, and then come back and check. I'm not going to do all the work required here. I'm just going to tell you what the answers are so that you can write it in the way that we would like. I did find this is geometric. I find a common ratio was -1/5. The absolute value of -1/5 is less than 1, so I passed the geometric test for convergence, which means I can calculate the infinite sum. The next one is not geometric. It is arithmetic. And I found that by calculating a common difference. And I got my common difference to be 1/4. Therefore, this series is arithmetic and will diverge. And I'm done. If you're divergent, I don't have anything, no further math, I throw you away. This is another I like when I get sigma series because I see the formula right here. I don't have to test for a common ratio or a common difference. My common ratio is pi/2, which is about 3.14-ish over 2. The absolute value of 3 something over 2 something is greater than or equal to 1, so I failed the geometric test for convergence, which means I diverge and I'm done. This series is useless to me. The next one, however, is not in sigma notation, gosh darn it, so I had to test it. I did test it. I found that my common ratio was 1/100. The absolute value of 1/100 is less than 1. Therefore, I passed the geometric test for convergence. Converge, and I used my sum formula, and the infinite sum was equal to 53/99. Okay. Kind of a repeating decimal kind of thing, yes? All right, so here, as you heard me kind of mention with the A and D in green, the infinite series passed the geometric test for convergence. So first, all we know right now is if we have a geometric series, it will converge as long as the common ratio is less than 1, the absolute value of it, because if I take the absolute value and the absolute value of the common ratio and then think about what the terms mean without them changing sign, so ignore the plus minus, just talk about the absolute value being -1/5, the terms are approaching 0. Now that's not enough terms, because remember, this is the sequence. The sequence of the terms are approaching 0. Right? So if the sequence of terms are approaching 0, I have a chance for a convergence. And the convergence, if you're geometric, is just indeed that ratio, absolute value of the common ratio, is less than 1. And so the sum then, if you graph the sum, even with those positive and negative, so this graph is not going to really make sense, right? But if you add negative 15 halves and 3 halves, and I'm not being completely mathematical, right? Then you add 3 halves and negative 3, right? Then you take that answer and add negative 3/10, right? This infinite sum will grow, but it'll grow to a bound, and it's negative, so this should be down further, right? Right? And it might waver in between here, but the overall shape is that the sum will grow to a bound, and that bound will be at negative 25/4. Down here, same thing. The sequence of the terms are approaching 0 because it's geometric with a common ratio that is less than 1. The sum will reach an upper bound. Right? The ceiling of the house, you won't bust out the house. And this upper bound is at 53/99. Compared to the arithmetic sequence, right? If I do the sequence of the terms, I didn't do a great job with my axes. Negative 7/4, the terms are decreasing with a constant rate of 1/4. The terms do not approach any value. I am not going to have a chance at all for the sum, right? The sum, you're going to just keep adding more and more and more negative, values. So if the terms don't go to 0, the sum doesn't have a chance. Same here. This situation is our a times b to the x, right? And this is a swoosh situation. Swoosh, the terms swoosh off, which means your sum, if your terms don't have a bound, right? They're getting bigger and bigger and bigger. Well, certainly their sum is going to get bigger and bigger and bigger. So the whole idea of knowing what the sequence of terms does is crucial to understand what your sum may or may not do. So far, we know that if we have a geometric series and the absolute value of the common ratio is smaller than 1, not only do our sequence of terms go to 0, but our sum will be bounded. So our sum will grow, but it'll be bounded. So today we are going to take infinite series beyond arithmetic and geometric. What if you don't have arithmetic and geometric series? How can you determine if they converge or not? So the test we have so far, right? We have the geometric test so far. We have the geometric test for convergence. You will converge as long as your common ratio is less than 1. We also have the arithmetic test, but the arithmetic test is really going to be wrapped up in another named test, and I'll show you what that means. So again, so far, what do we have? If your series is arithmetic, you automatically diverge. if your series has a common difference, right? Your terms grow without bounds, so your sum does not even have a shot at reaching a bound. Same thing, and I want you to think linear here, right? Your terms are linear. The sequence is linear. So the limit of the sequence as you go to infinity, as you go off to infinity, is either positive or negative infinity. If the absolute value of your common ratio is greater than 1, you also, even if you're geometric, right? You're geometric, but your common ratio is greater than or equal to 1, you have the swoosh situation. I want you to think, right? Exponential swoosh for your terms. The sequence of the terms swooshes. So if your terms go off to infinity, your sum has no chance to have a bound, and your series will diverge. However, if your series is geometric and also the absolute value of your common ratio is less than 1, not only do the sequence of your terms approach 0, so your sum has a chance to be bounded, you are guaranteed that your sum will be bounded. And we call that series converging. Sequence of terms goes to 0. If you're geometric and your common ratio is less than 1, you pass the geometric test for convergence, and your series converges, and you get a number using this formula. You get a number for that bound. You can kind of sort of think of this situation here where you are geometric, but you fail the geometric test for convergence because your sequence of terms does not go to 0. Or conversely, I mean, you can also think of obviously the common ratio being greater than or equal than 1, so your sequence of terms will not go to 0, is what that means, right? Arithmetic is, and this is actually a test for divergence. It is the only test for divergence. So I want you to look at this picture. This picture is a nice kind of like thought of folding one piece of paper. You have one square. Think about folding it in half, and then folding the half of paper in a half, folding that fourth of the square in half, folding that eighth of the paper in half. This sequence is one square cut in half, then a fourth, then that is cut in a half, then 1/8 is cut in a half, and so on, so on and so forth. That is the sequence. There's your sequence. Hopefully you can see that your sequence of terms does go to 0. If I look at the series, the series takes the sum of that 1 plus a half plus a fourth plus an eighth, and adding smaller and smaller numbers. And hopefully you can see that that is right? Actually, let me take off, right? You can figure out that this sum is geometric, right? Where I take each of those fractions as 1/2 raised to the n in summation notation. I would need to start at 0 to get that 1. So since this is a geometric series, the terms of the sequence went to 0. I also had a geometric series. I identified my ratio was equal to 1/2. The absolute value of 1/2 is less than 1. This infinite sum will grow, but it'll grow to a bound, and further, that bound is 1 over 1 minus 1/2. Which is 2. Crazy, right? So the series, the graph of the series, would kind of sort of look like this. Right? And you could keep adding and adding and adding, but the amount of values that you're adding are so infinitely small that you will never grow above 2. There's a very famous paradox in math, or philosophy really, where this, before they called it math, they called it philosophy, where if you, your distance to the door, you calculate your distance to the door is 1 foot, and then you walk halfway to the door to get to a half, and halfway then of your remaining to get to the door, and you keep cutting your distance in half, you will never get to the door. I mean, if you kind of think about that mathematically, looking at all of these fractions, right? All of these fractions, their numerator is 1, right? To get a fraction to be equal to 0, you can't have 1 in the numerator all the time. Crazy. All right, so what if we are not geometric or arithmetic? How can we test to see whether our series converges? Convergence is what I'm after, and yet here I am starting with your very first test to be a test for divergence. Told you only have one test for divergence, and before we've called it, and it is just that, and we referred to the arithmetic sequence or arithmetic series, and the nth term test works on the arithmetic sequence, but it works on any other sequence that is not arithmetic but has one characteristic like an arithmetic. And what that means is if the terms of a series, right there, that means sequence. If your terms do not approach 0, then the series doesn't have a chance to converge. So you are automatically divergent. So of course, that works for arithmetic. We have an arithmetic sequences are linear. So the sequence of their terms either goes off to infinity or goes off to negative infinity. Right? Their terms, the limit of their sequence goes to infinity, so no shot at diverging. No shot at converging. But there are other series whose terms don't go to 0 that might not follow a linear pattern. I mean, for instance, my geometric swoosh situation, right? It's just that I can think about the geometric test. I don't have to think about the nth term test, but, right, 7... right? This series diverges because of the nth term test for divergence as well. It just was easier, and we're used to looking at the geometric. But what about this series? That's not linear, right? That's not an arithmetic sequence. But what about its terms, its sequence of terms? It's a freaking parabola, right? What about x cubed? Right? What does the sum of x cubed do? What do its terms look like? Well, kind of looks parabolic, doesn't, after 0. But, right, the idea is that if you write out some terms of a sequence, of a series, right, and you look at the terms, in other words, you look at the sequence, if the terms do not approach 0, you got no shot. Throw it away. You're done with it. This test is so easy to run, and the other tests can get pretty nasty. Sometimes kids forget about this. So look at this series. Now what's nice is they gave me the rule here, so I don't have to generate some terms. But if I look at the rule, right, I'm like, what the heck is going on? This is how I generate the terms. Look at that with your function brain. That is an n to the first over an n to the first. What are the limit of the terms? The limit of the terms as you go to infinity, right? The limit of the terms is the limit of this rule, not the sum, the limit of the sequence, and the limit of the sequence is 1/2. So automatically I can throw this series away. Diverges by the nth term. Always run this test first, unless it jumps out at you that it's geometric, right? And this holds, the reason we don't call this the arithmetic, because this test holds, right, every arithmetic series, the terms do not approach 0. But I had to look at this one. It's not arithmetic, but the terms do not go to 0. Therefore, this series diverges. It will grow without bound. It busts out the house. Now be very, very careful. Don't use this test backwards. This is not a test for convergence. Students make this mistake very often. Don't do this. Don't even write it down. If the terms do go to 0, you cannot assume convergence. This is not a convergence test. Right? Don't do this. No. No. This is not true. If your terms go to 0, you have a chance to converge, but it is not guaranteed. If your terms do not approach 0, then the series definitely does diverge by the nth term test for divergence. Okay, so I don't know how many of you have done logic before, but this is a P arrow Q logic statement, right? Conditional statement, if then. If you know if then is true, does not guarantee that the opposite of P guarantees the opposite of Q. That is not true. Right? Not true. I put up this, the converse, right? That's converse. The converse also, right, is not true, right? Be careful. Whoops. Converse. Just because a series diverges, the converse is the opposite, right? If a series diverges, then the series, then the sequence, the terms of the series don't approach zero. This is also not true, right? You can have and we're going to look at it next, it just hasn't happened to us yet. You can have a series whose terms do go to zero and you still don't converge. So be very, very careful. The nth term test is just for divergence. If the terms don't approach zero, done. If the terms do go to zero, it better be, so far, geometric with a common ratio whose absolute value is less than 1. So, what happens when our terms do go to zero and it's not geometric? Well, another very famous kind of series is called the P series. P is for power. So copy this down. P is for power. I can't prove this for you this year, but I will prove it to you next year with something called an integral test. So for now, you just have to take this on faith. This is a theorem that if you have a P series and you have positive 1 always in the numerator, so you have to match this form, and then you have, technically this is over 1 to your power. This kind of series, called a P series, will converge as long as your power is greater than 1. But will fail the P series test for convergence otherwise and then diverge. So for example, this series, now notice the sequence of the terms does go to 0. 1, 1/2, 1/3, 1/4, 1/5. The terms do go to 0, right? The sequence goes to 0, but not fast enough. Not fast enough. That's kind of a weird concept, but it doesn't fall the terms don't fall to 0 fast enough because your power is only 1. And again, there's going to be more about that next year. This is actually a super famous series called the Harmonic Series. Maybe some of you have heard of it before. Yes, there is a music application to the Harmonic Series. But it does mean that even though the numbers are getting smaller and smaller and smaller, when you add those numbers, it doesn't grow linearly, it doesn't swoosh, but it still goes to infinity. There is no bound to the sum. Even though those numbers are getting smaller and smaller and smaller, they're not getting smaller fast enough to stay within the house. However, if you just have make your power 2, that sequence also goes to 0. But it goes faster to 0. Faster. Rate. Sequence does go to 0, but this series converges. The numbers, when you add them together and add infinitely, 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 it will reach a bound. What's super, super important here, though, is that I don't know what that number is. And even when we get to calculus, there are some series that aren't geometric that we can find the sum, but actually it's much more common just to be able to say the series converges and not to what number it converges. So that's a hint for you on an assessment. If somebody asks you, does this infinite series converge, and find the sum, it's got to be geometric or you can't find a sum. You can't. All I can tell you here is that this series does converge because it passes the P-series test. It is a P-series. P is equal to 2, which is greater than 1, therefore converges. Done. I'm going to keep the series. I'm not going to throw it away, but I can't tell you the sum. When P is a half, you identify that you have a P-series. You say P is equal to a half. But since P is less than or equal to 1, your series diverges, and you know this series is no good. Even though the sequence goes to 0, the sum will grow slowly, but it will continue to grow out the house. What's kind of cool is that Euler was able to find a sum for this P-series, right? And it was pi squared over 6, an irrational number. Crazy, crazy with pi. Pi just pops up all over the place. Pretty cool, huh? All right, so notice what's missing from these directions. Does the series converge? And nobody is asking you about the sum. They're just saying, does the series converge? So hopefully you recognize each one of them as a P-series. So this is a P-series. So you need to tell me it's a P-series. It's not geometric or arithmetic. It is a P-series. P is equal to 3, which is greater than 1. Therefore, I pass the P-series test for convergence. I'm going to skip down to this one and write the same thing. I've identified a P-series. I've identified P is equal to 5 halves. 5 halves is greater than 1. Therefore, this series converges. You do not find the sum. You can go try to find Euler and ask him if he can do it with something, but he's only done 1 over n squared. Don't know what he's doing right now. He's super dead. But what about the other ones? I have identified that I have a P-series, but P is equal to 1/5. You need to be able to unradicalize that from your exponential days. This is less than or equal to 1, therefore you fail the P-series test for convergence, meaning you diverge. Right? What if this had been written, what if, be careful, right? That's why you do exponents before you get here. What if this had been written as 1 over the square root of n to the 5th? Or what if it had been written as the square root of n to the 5th? All to the 5th. You need to know that all of these things mean n is n to the 5 halves, which is a P-series. Ooh, look at this one. This is kind of weird. This is a P-series because I do have a power there. When will this P-series converge? Well, it's when the power is greater than 1, so for in this case, p needs to be what? Just greater than 0. Right? That's just because of the way this is written. Even if p was 0.00001, you would have a convergent p-series. Again, no one can ask you for the sum of an infinite p-series that converges. Now, let me throw, I'm going to write next to here, this one converged, this one converged, and I'm going to change this one to 1 over, let's say p is 3 in this, so I'm going to change this one to 1 over n to the 4th. And since, right, that's what I'm going to change this one to, and say this one converged, and this one diverged, right? Failed the p-series test for conversion because the power was less than or equal to 1. What about those ones? So, notice the similarity. I want to say these series, I really would like to say that this series converges. It's super close to this one. It's almost a p-series, and p is greater than 1. Why can't it converge too? Notice that in each one of these cases, and that's, can you see now why I changed this to 1 over n to the 4th, so I could have this similarity here. You have super similar series. You have almost a p-series. So I know what to do if I have a p-series now. So it's not arithmetic, it's not geometric, but it is a p-series. Got it. But what if I have a series that is really close to being a p-series? This technique is also going to work for what if it's really close to geometric but not quite, but that gets a little bit messier. So for now, we are just going to deal with what if you have a series that is really, really close to being a p-series. It's similar. So similar to me isn't like your, you know, it's not like your sibling. It's not like your sister or your brother, but it's like a cousin, right? What if 1 over n cubed and 1 over n cubed plus 1, they're cousins? So remember, I'm looking at their terms, right? That's the first thing I do is look at their terms. So the terms of 1 over n cubed go to 0, which gives it a chance for the series to converge. And then because it's a p-series, I know that I do converge. P-series with p is greater than 1, right? But now I'm sticking just with the sequence here. Look at these terms. Now I'm going to write out a couple of terms over here. 1, when n is 1, this is 1 over 1. Then 1 over 8. Then 1 over 27. These terms are 1 over 2. And then I'm going to put 2 in here, and I'm going to get 1 over 9. And then 1 over 28. Isn't it true that the terms of the cousin are always under the terms of the original? Isn't that true? Right? Here are my cousin terms. Here are my original terms. Isn't that true? I'm going to skip down to the bottom, and can you see that the same thing is true for the bottom? The terms of 1 over n to the 4th approach 0. So I know I have a chance for convergence, and then 1 over n to the 4th does converge because the terms are always smaller. I'm sorry, because it's a p-series where p is less than 1, but 1 over n to the 4th plus 3, I mean, just write out a couple terms. The terms are always under So what does that mean for the sum when we went to the series, right? When we went to the graph of the series, and I'm just going to draw that up here, the original series, because it's a p-series where p is greater than 1, the original 1 over n cubed, the sum grew to a bound. But since the terms of the cousin are all less, the sum is going to be less, isn't it? So the sum is going to be under. Because I had similar behaving functions as I went off to infinity, because I had cousins, and further, because the cousin always was smaller than the original, you are allowed to conclude that the cousin converges too. So let me write that out. I'm going to erase this and I'm going to write out what I just did. The first thing I had was I was given this function and I realized it had a cousin. And further, the cousin converged because it was a p-series where p was greater than 1. Further, the cousin was always bigger than, or equal to, could actually be equal to, right? My unknown, right? This is my unknown. I didn't know what to do with this guy, but it was super, super similar to the original. The original converged was a p-series because p was greater than 1. The original function was always on top of, the terms were always on top of, so the sum is always going to be on top of. Therefore, my unknown function converges. I can't say by the p-series test. But by the direct comparison test. So if you're not going to do an official p-series test, here are the things that you must do. You must tell me who you chose as your original. Step 1, choose your original. How do I choose my original? I find the p-series piece of my unknown. 2, you have to tell me what you know about your choice. It converges. Here's the most important step. Position. If your known function converges, your unknown must be under it. Your unknown must be smaller. Has to be so. Or you can write this, but it's nonsense, and you get no credit if your position is wrong and you're trying to make a conclusion. Your 4th is your conclusion, and your 5th is name the test. Okay, so let's skip down here, and remember I had changed this to a 4, and let's do the same thing here. We've already drawn the graph here. Step 1, choose. So you look here, and you say that looks an awful lot like 1 over n to the 4th. So choose the series 1 over n to the 4th. Second, tell me what you know about 1 over n to the 4th. Next, write out a few terms or look at the graph of the terms, right? You could just put this into y equals. Put 1 over n to the 4th into y equals 1 and 1 over n to the x, I guess, from your calculator to the 4th plus 3 and look at them. Now you have to zoom in your window, but look at them and make sure, since your original converges, step 3, you must say that the one that you know is above or equal to the one you don't. Then I can say, therefore, the one that doesn't fit into the p-series pattern still converges because it is so similar, so similar. And yes, you can write DCT. Okay? So that's the direct comparison test, which is another test. It really uses the p-series test, right? Yes, we can compare to other kinds of functions, but at the very beginning here, right, we're just learning, you're always going to be comparing to a p-series. Now notice I haven't talked about the other two yet. So remember, this one diverged. So somebody asked me about this series, and I said, hey, that looks awful familiar to a p-series that I know. So I made a choice. Next, I said, what do I know about the choice? This p-series diverges because it is a p-series where p is less than or equal to 1. And next I have to show position. So here, the terms of these terms do go to 0. This is the terms of 1 over n to the 1/5. But what's true about these terms? Well, this is true, right? 1 over n to the 1/5 is bigger. So this statement is true. And it is still true that 1 over the 5th root of n plus 3 is under. But because my known function diverges and my unknown lies under it, there's no conclusion possible. With the direct comparison test, the position isn't right. This is a true statement, but it's not right. If your original function diverges, your unknown function, kind of think about this, like this is completely mathematically incorrect, but kind of sort of think of the swoosh, right? You know that if this, even though these terms go to 0, the sum is going to shoot off, right? The sum is going to shoot off to infinity. Goes slowly, but it's still going to go to infinity. So therefore, the one that lies underneath of it, right? I don't know. I don't know. I can't tell. The position is wrong. My statement is right, but the position is wrong because my original diverges. Crud. Here's what that picture looks like. So I went ahead and I did put this into my calculator, right? And I captured just the top of the screen. So this right here is the original, the terms. This is just the terms, not the series. The terms are going to 0 of 1 over n to the 1/5. it is on top of right? And the purple sum swooshes off, so I can't make any conclusion about what lies under. Again, up here, my original function, I had the same situation up here. My original sequence, right, was coming down to 0. And I'm just making it connected as if I had put it into my calculator. But the important difference is what I knew about this one. This sequence is going to 0, and the series converges. So the unknown one that lies underneath of it kind of gets caught. Think about the light blue function collapsing on the dark blue. Whereas here, the known function shoots off, so I have no conclusion possible about what lies under it. Sadness, sadness. DCT doesn't work here because of position. Oops, sorry. Huh? The direct comparison test is inconclusive because the position didn't match. Come on, pen. Inconclusive. Because the position didn't match, right? The statement I needed to make. So let's see what's going on here. Remember, this one diverged. I'm sorry, converged. This one converged because it was a P series where P was greater than 1. So I think about the terms. The terms do go to 0, and because of the P series test, the sum reaches a bound. So step 1, I made my choice. And do you see why I made my choice? This is actually 5 times 1. There's my choice, 1 over n to the 5 halves, which is a P series, converges because P is greater than 1. So I told you what I know about my choice. Since I'm converging, I need my position statement, right? What I need to happen is I need it to be true that since my original choice converges, that my unknown is smaller. I need this position statement to be true. But if you write out a few terms or you look at the graph, uh-oh. Here is this graph, right? And again, the terms it's supposed to be not connected, but I just got lazy and didn't do it. This is 1 over n to the 5 halves. I know its series converges because of the P-series test, but look at my unknown. My unknown terms are what? Crap, they're above. So I know this one, think of this as collapsing. It doesn't tell me anything about this, about the function that's above it, right? Or the sequence that's above it. So this one, the DCT, was inconclusive because my statement wasn't wrong. Remember, up here it was true that the known was bigger than the unknown, but the known diverged. right? So think of it as shooting off, so I couldn't say anything about what was underneath. Here, right, the known one does converge, but the unknown one is on top. So my position equation, this statement was wrong. This is the statement which is inconclusive. Position was not right. This is super annoying. I have a way around this. But first, before I do, let me give you the formal. Anyway, I couldn't write. The DCT is inconclusive here too because position was wrong. Here's formally what the direct comparison test looks like. Oh my God. You have to have the positive terms if you know, right? If you know that you have, if each term, so I'm dealing with the sequence, if each term of the series is smaller to some known positive termed convergent series, then your unknown will converge as well. The series, the unknown series, will diverge if the sequence is bigger than a known divergent series. So, the direct comparison test. If the function, if the series you know, your choice, if the series you know, the choice converges, the position of your unknown needs to be under. If the position of, if your known choice diverges, then your unknown has to be above in order for you to be able to use the direct comparison test correctly. So, this is kind of like my algorithm. Choose a similar behaving series, right? You have to make a choice. Tell me what you know about your choice. Make sure you have the correct position, write out terms, or look at a graph. Again, what I just wrote out before, if your known function converges, the unknown must be under it. If your known function diverges, the unknown must be above it. Then write out your conclusion, and technically this is step 4 and 5 because this is, right, you can't just say converge or diverge, you have to name the test. So take a moment and try these. Step 1, choose. And I'm going to get super lazy here and drop the sigma signals things. You can too. Tell me what you know about your choice. Tell me about position. Now this is where you have to take some time and make sure. And honestly, here's what I do first. I write out the statement that I want to be true. So I'm like crossing my fingers. Since my known function converges, I want my known function to be on top of my unknown function. So I write out what I want, and then I cross my fingers and I look at a graph or right? I look at a graph or I write out some terms and I verify this is true. It is true in this case. So then I can say step 4, this unknown function, and here I will be better, converges by the DCT. Okay? Try the next one. Who are you going to choose? First, I'm going to rewrite this. Multiply this times 1. Make your choice. What do you know? This is a P-series where P is less than or equal to 1. Therefore, we know what? Diverge. So, write out your position statement and cross your fingers and hope it's true. What is the correct position statement? Since 9 over 2/3 diverges, 1 over n to the 2/3 diverges, I need it to be under 9 over n to the 2/3. Look at your graph, verify that is true, and if you're ever running out of time on an assessment, just hope that's true. Now again, I can mathematically think about this, and here I'm going to show you a way to achieve this kind of function. This kind of series. I can't do that here with this +1 issue, but here this is a multiplier. I want you to use some of your sigma properties. Write this as 9, osmosis it out there. I'm so very clever. I don't really need the DCT here. I can just use sigma properties and say, hey, what's up? That is a P-series. That P-series diverges, and you know what? If you have a divergent series, guess what 9 times a divergent series is? Snap, diverge as well. So I actually wouldn't use a P-series on a multiple like this. I wouldn't use the direct comparison test. I wouldn't use, oh no, not going to say that yet. All right, we have another test. The limit comparison test is more annoying with the math, but the benefit, this is like the con. The con is that there's more math in the limit comparison test. But the plus is the position don't matter. I don't have to worry about, oh my gosh, converging has to be under, diverging has to be over. Oh my gosh, which way do I write that inequality? I have to verify, I have to look at my graph, I have to blah, blah, blah. The limit comparison test is used for the same kind of comparison, cousin, or similar behaving functions. But I don't have to worry about position. So I'm going to go all the way back to this scenario, this situation, where remember for these two, the direct comparison test was inconclusive because the position was wrong, right? I couldn't use the DCT on this one. So I might want to use the LCT on this one. The limit comparison test doesn't matter about position. All that matters is that you are doing a comparison, so you still do need a similar behaving function. So to do the LCT, the first thing you do is make a choice. Choose a cousin, the similar behaving function. Just like the DCT, you tell me what you know about your choice, but then your step 3 is not position. Because for the limit comparison test, either the position doesn't work out or it's too annoying to do. So step 3 is take a limit of a ratio of the sequences. If the ratio of if the limit of the ratio of sequences is a number, not an infinity, if your limit equals a number, then both functions, both series do the same thing. And I'll write this out a little bit better. Right, when we do these examples. So don't worry about, this is going to go away, but don't worry about it yet, because I'm going to give you a slide with all of these written out. So what that means is we already know, right here we have one, our choice, right? We made our, this is the series over here. I want to know, does this series converge? That's my question. So I chose a similar behaving function. I told you my known function diverges, right? And I already wrote this out, P series, P less than or equal to 1. The position thing didn't work out, so I need to make a limit as you go off to infinity of the ratio of the sequences. So my two sequences are my unknown, and it doesn't matter who, right, who's the numerator, who's the denominator. It does not matter at all. Clean this up. Times the reciprocal. And then use your rational function brain. Your numerator has the exact same power as the denominator, which means as you go off to infinity, this limit is the ratio of the leading coefficients, which is 1. Since your limit is a number, both series do the same thing. Well, go back and tell me what you knew about your known function. So my unknown function diverges by the limit comparison test. Crazy, right? I know, I know. Stay with me. Stay the course. Does this series converge? Step 1, make a choice of a similar behaving known function. I keep saying function, series. What do you know? We know this converges because P is greater than 1. Set up a limit of the ratios of the sequences. Again, it does not matter which one is the numerator. I generally make the more complicated one the numerator, but it doesn't matter. Clean that up. Use your rational function brain. The numerator has the same power as the denominator, so the limit is the ratio of the leading coefficients. That limit is a number, therefore they both do the same, both series do the same thing. What did your original do? Go back, your known function converged, therefore my unknown function converges by the limit comparison test. OMG! So let me go ahead again to the slide that actually spells out officially what the limit comparison test says, right? This is what you see why I didn't show it to you first. It's kind of scary. If the limit of the ratio of the sequences, if the limit of the ratio of the sequences is a number, and that number is between 0 and infinity. Okay, so obviously you can't equal infinity, so the only number that is bad is 0. Right? I didn't say that before, I just said it needs to be a number, but that number can't be 0. Right? It can be any other number, positive, right? And you really are doing positive values, so you're never going to get a negative limit. So it just doesn't matter as long as you do the limit of the ratio of the two sequences. And one of these sequences is from a known series, and one of them is unknown. If you get a number that is not 0, for that limit of the ratio, they both do the same thing. Now, here's the thing, the LCT, if you do get a 0 or infinity, it doesn't necessarily mean abandon the limit comparison test. It may mean that your choice was just not a good one. It just means that your choice wasn't similar enough. So go back and look and see if you missed something with your choice and adjust, and then you can try it again. With the direct comparison test, as soon as my position was not right, I was kind of out of luck. So, step 1, choose a similar behaving series. Tell me what you know. Then do the limit. Did you get a number that is greater than 1 but not infinity? If that is true, then you can conclude diverge, then they either both converge by the limit comparison test or they diverge by the limit comparison test. So let's look at these ones. Okay, these are the ones that right, I did this one with you already, right? Right, if you go back and look at, right, we did this one. This one didn't work with the direct comparison test, so the first step was choose. We chose 1 over n to the 1/5. We said what we know. Then we did the limit of a ratio. Again, my choice is to do the more complicated one in the numerator. clean it up. And yes, you can go right to this step if you like. Notice that with my rational function brain, I've got a ratio of n to the 1/5 over n to the 1/5 as I go off to infinity. This 3 doesn't matter. My limit is 1. 1 is between 0 and infinity. Therefore, they both diverge. They both are useless to me. So this is one we haven't done before. And this is one where the limit comparison test, if you're not careful with your choice, things are going to go awry. So I want you to use the limit comparison test on this, and you might be, and I won't blame you if you choose 1 over n to the 4th as your known. You know it's a p-series. So you know it converges. Oh, this isn't right in here. Pen freaking out, pen freaking out. So over here I'm going to do the limit. Right, the more complicated one. And then again, you can do this. But what is this limit? Notice I have n to the 5th over n to the 4th. This limit goes off to infinity, right? Because the numerator is more powerful. So I think to myself, sadness, sadness. The limit comparison test is not applicable. But if you go back and look at your choice, you chose 1 over n to the 4th, but look what happens here. N over n to the 4th, maybe this was a bad choice. What does n over n to the 4th actually reduce to? Remember, you're going off to infinity. This -3 doesn't matter. Oh, maybe I should have used 1 over n to the 3rd. That doesn't change this. I still have a p-series. P is greater than 1, I converge. But now, notice that when I've got here is my unknown, and then remember I'm doing the ratio of 1 over n cubed. Right, so I'm going to actually multiply by n cubed over 1, and now look at what happens. This is n to the 4th over an n to the 4th, so your limit is equal to 1, and 1 is bigger than 0, but not infinity. Therefore, my known function, which converges, does the same thing as my unknown by the limit comparison test. OMG. OMG. I know this is a lot of information. It's okay. We're going to take a while to practice this. All right, last test, the ratio test for convergence. I need to tell you that the ratio test is pretty famous. When next year you do the ratio test, AP absolutely loves the ratio test. You will use it a lot. The ratio test is the most mathy, which is why AP uses it the most. Don't write this down, but don't let it freak you out, okay? I'm going to explain this and I'll take you through it. So again, think sequence. These are terms of a sequence, right? Because your sequence is what you're summing to get a series. This is not the limit comparison test. You're not making you're still taking the limit of a ratio, but you're taking a ratio of adjacent terms in the same sequence. This is not comparing. You're not comparing at all. You're not comparing two different sequences. You're comparing terms of the same sequence. The ratio test is desperately trying to be the geometric series. If you get, and that's why the limit is called an R. R for ratio, it's kind of sort of like thinking about a common ratio in between adjacent terms. Shocker, look at that conclusion. This looks very similar to the geometric series, doesn't it? There's one critical difference, though. The price you pay for trying to force a series into the geometric test when it's not really a geometric series is that the ratio test is inconclusive if your common ratio, which again isn't really common, it's because it came from a limit. The limit of the ratio of adjacent terms is equal to 1. Okay? It means I have to go try a different test. The ratio test didn't work. All right, so let's see what this looks like. Since this is the most mathy, we try to do other tests first. So I'm telling you to use the ratio test for convergence on this. So I gave you some terms. More importantly, I gave you the pattern. Here is a rule of thumb. It's not a mandate, but if you see exponents in your, right, if you write this as an exponential expression, 2 to the n, it's not an n squared, it's not a p-series, probably the ratio test is going to be necessary. So here's how I use the ratio test. Set up your limit. So you need to take the ratio, and you can't use these, you have to use your pattern. What is the next term? The next term, isn't the next term n plus 1 over 2 to the n plus 1? So you need to make a ratio of these two terms. So here, put n plus 1 over 2 to the n plus 1 compared to n over 2 to the n. Again, it doesn't, right? This time it does matter. You have to put the n plus 1 term in the numerator. Clean this up. And now use algebra. Look at what I'm going to do here. See how clever I am. Multiplication is commutative, right? So I can put this in any order I want. So I'm going to put the n first and then check out my algebra skills. Oh, snap. What happens to the 2 to the n's? Bye. Remember, I'm now taking a limit, and I want you to look with your function brain, your rational function brain. I want you to look at the power on n is the same as this power on n. So the limit is the ratio of the leading coefficients. Coefficient here is a 1. What's the coefficient down here? This is my r. My r is less than 1. Therefore, the series converges by the ratio test. Oh my Lanta. So what were my steps here? My steps were 1, set up the limit. 2, use your definition of division to make your limit a multiplication. 3, algebra. 4, talk to me about the ratio. 5, make the conclusion. Wow. Now notice here I told you what test to use. I'm going to do that, right? I'm going to tell you every time what test to use, right? You're just starting. You don't have to make a decision yet. Not just for the ratio test. I'll tell you for each one, right? Well, let me back off. Probably won't say it for geometric or p-series, but I will tell you to use the direct, the limit, or the ratio test for your home for the foreseeable future. Whoa, somebody's yelling at me. Oh my Lanta. That's another clue. I will tell you to use the ratio test, but I want you to notice that the ratio test usually is reserved for when you see, or you need to use it, other things won't work when you see exponentials or factorials, and mixed in probably with powers. So notice I have an n to the first, a 2 to the n, and a factorial. I got everything here. So what's step 1? Replace every n with an n plus 1. That's divided by the original. I'm going to always skip right to this step. You can or not, but division is the same as multiplication by the reciprocal. Okay, so that's my first step. I'm going to take this limit. I really did step 1 and step 2 in the same one, right? I did 1 and 2 together, which I always will do. But you need to make sure that it's the n, unlike the limit comparison test, it matters. The n plus 1 version has to go first. Now I'm going to do algebra. Make one big long fraction because I'm multiplying 2 fractions. There's nothing to be done here. This is n plus 1, but notice what I'm going to do here. And I'm going to leave this alone for right now. Multiplication's commutative. So I'm going to put the n over here, matching up with, right, polynomial looking things. Exponential looking thing here, and then notice this is n plus 3, right? This is n plus 3 for factorial, but what it's factorial noted, right? Factorial information. This is n plus 3 times, oh snap. Now start simplifying stuff. What happens here? 2 to the n divided by 2 to the n, bye-bye. n plus 2 yelling divided by n plus 2 yelling, bye-bye. What do I have? 2 times n plus 1 over n times n plus 3. Right, so what do I have here? I have an n to the 2n to the first situation, and here I have an n squared. What is your limit as you go off to infinity when your denominator is heavier? Right, this is an n to the first over an n squared. My limit is 0. Uh-oh. Uh-oh, doesn't that mean something bad? Oh, wait, don't mix up your tests. The limit comparison test, your limit can't be 0, but this is the ratio test. This is my r. My r is less than 1. Therefore, since my ratio is less than 1, right, the ratio I got from my limit is less than 1, then this series converges by the ratio test. Let's try another one. One and two together. The limit. Replace every n with an n plus 1. Divided by, which means I'm going to multiply by the reciprocal. Clean it up. That's a quadratic, right? Right, this is 2n plus 2 minus 1 times n. Clean this up a little bit. So, right, this is a 2n squared, blah, 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 over, what is this, 2n plus 1. Oh, this is also a 2n, right? Did I do that right? 2n plus 1, right? This is a 2n squared. What's this limit? Oh, this limit is a 1. Uh-oh. What test am I doing again? I'm doing the ratio test. This is not a limit comparison test, right? Those are the things that cause kids issues. The limit comparison test has a limit, and the ratio test has a limit, but the results of your limit mean different things. Look back at your notes. If you're doing the ratio test and your limit is 1, it's not bad necessarily, but it doesn't mean anything, so I guess that's bad. The ratio test is inconclusive. Oh, rats. That means I did all that work for nothing. Now, if you think about this, if you look at something we did earlier on, I took you through this because, remember at the very beginning, I said before you run, now it's not fair because I told you to use the ratio test on this, but this was a trap. Sorry. This was a trap. Remember I told you to always run what test first before you do any test. Now, if the directions say use the ratio test, you gotta, right? I want to see if you know what it means when you get a 1. But in reality, if I was doing this for real, somebody just asked me about this, hello, look at that sequence. I would have used the nth term test for divergence on this, would have concluded divergence right away and thrown this series out, right? The limit of just these terms themselves are 1/2. the limit of this sequence is 1/2, which means the terms don't go to 0, which means you don't have a shot to converge. Right? So the ratio test was going to be inconclusive. I knew that from the beginning. But it's important, right? There's no way when you're just starting that that's obvious. But can you see that this is going to be the same situation? Again, what if I didn't say use the ratio test? Because if the directions say to do it, you gotta. But if I just said, does this series converge? Right? Is it geometric? Is it arithmetic? Oh my God, look at the pattern. It's not really any. There are other things I could do though, right? I could firstly look at the nth term test. That's something I could do that would be quick. The limit of the sequence goes to 1/5. Oh no, what am I? I'm an idiot. No, the nth term test isn't any good because it goes to what? Goes to 0. Okay, so the nth term test isn't good, my bad. But what else could you do? For melting your mind. Oh, I'm sorry. I wanted to make sure that you saw this. So here is a nice little flow chart. Procedure for determining convergence. The first thing you want to do is look at the nth term test, right? Try to get in the habit of always looking at that first, because in reality, you're going to be, right, not really told what series, right, which test to use. You're going to have to decide yourself eventually, not now, but eventually. So if you're just thinking about it, right, always think about the nth term. Do the terms of the sequence go to 0? If they don't, it can't diverge. I'm sorry, it can't converge, and it automatically diverges. So that's first, right? Is the limit of the terms 0? No, diverge, move on. If the terms do go to 0, you might converge. Maybe you can't tell if the terms go to 0, so maybe they do. The next thing you do is go to geometric, right? You're running down the list. Is it geometric? Because geometric tests. If it's geometric and you can see your common ratio, well, yes. Converge if the absolute value of the common ratio is less than 1. Further, this is the only one that you can give me a sum for. If it's not geometric, maybe it's a p-series, right? Are you in this form where the numerator is a 1 and then you have n to a power? If that's true, your series converges as long as p is greater than 1. I have a series that is almost a p-series. Almost a p-series. Compare to a p-series with a similar degree using either the direct or the limit. Again, I will tell you which one to use for now. If a comparison doesn't work, right, if I don't have anything that is similar enough, or again, you see exponential terms, right, you have an exponential pattern, a factorial pattern, or lots of different powers combined with exponentials and factorials, well, then use the ratio test. Okay, and the only thing you have to watch out there for is if your ratio is 1. Right? Remember, for the limit comparison, your limit had to be between 0 and infinity. Here, for the ratio test, we call your limit the ratio. And if the ratio is r, is the only thing that is a dagger. So this is a really nice flow chart. Also, here are some cool videos, right? This one here, I captured this part of the screen because I thought this lady is hilarious. This takes you through a nice animation of the idea and the concept behind infinite series and converging. And then Vi Hart goes through some really nice esoteric kind of like thinking about infinite series, right? It's kind of cool, right? If you know who Vi Hart is, she's awesome. All right, so now I am really saying goodbye.